Let's look at what happens when you invest your money not as a single lump sum in a compound interest account, but progressively every year the same amount. That's called an annuity. And here's a spreadsheet that's going to set that up, and it's going to tell us what the numbers are, but then we want to get some sort of closed formula, a shortcut formula. So here I've got a space to put what you're going to put in each year. I've got the annual interest rate, and I've got, often it's nice to emphasize the multiplier, that's 1 plus the 0.05 interest rate, so 1.05, and that's what's really driving the formulas we're used to for ordinary compound interest. So notice what happens at the start. I've got zero money at the start of year one. I haven't put in my $1,000 yet. I don't get any interest on it, but then I put in $1,000 and I've got $1,000. Pretty boring. Now it's year two. I've got $1,000. I get $50 interest on that. I also put in $1,000. Now I got $2,050. In the first few years, you're not getting a whole lot of interest. Well, it's not trivial. And most of the growth is because you're putting in this constant $1,000. It's going to be similar to linear growth, not exponential. 45 years later, I've got a split screen going here. You've got a lot more money, therefore a lot more interest at the same rate. And now that's dominant, and the additional deposit you're putting in, again, while not trivial, is not as significant. So here, it's kind of like I could erase the thousands and I would get something that should look fairly exponential. Turns out if you graph this on a semi-log graph, it starts out steeply because proportionally you're putting in a whole bunch of money compared to what you have over here. Um, and then it actually bends and becomes a straight line, or pretty close to a straight line down here. But we want a formula that really matches this in a precise way. So real quick, let's make sure we know how to write in sequence notation and Excel notation just straight up compound interest. What about if you just put in $1,000 at the start, same interest rate, for example, same multiplier? We know that formula. We know how to do this, and let me go over to another program to make sure we know how to do it in two different mathematical notations. So here's how we've seen it before. We were emphasizing the idea of exponential functions, and we had a time variable here that theoretically could be any real number. It's actually kind of unrealistic in the money situation because the money comes in discrete lumps and actually doesn't change smoothly. So P times the quantity 1 plus r to the t, that's going to become sequence notation. A sub n is going to be, we can still call it P, okay? But then times little r to the n. That will be one version. That's if after n years we've had the multiplier go n times, or we have seen that often things work out nicer if you've got an n minus 1. And there'll be a bit of a playing with the n and n minus 1 here, but I hope it's not too distracting. So it's just the sequence notation. Oh, and I'll highlight this one maybe. For compound interest. And if you want to call this one a sub 1, that's totally fine. It's just equal to p in this case. Okay, so how does that look in Excel notation? We've done this before, but I want to make sure it's all set to do in the other cases. Here we've got equals, we've got $B $2, and that'll light up, that's the principal, times, and then I could either do 1 plus this, or I could do the multiplier. And I'm going to actually do the multiplier because the multiplier is little r. And so little r is going to be here $G $2 to the, and then just the number of years. Now this is the tricky bit, of course. Should I put in an n or n minus 1. Here, what I'm going to do to match up better with other stuff, I'm actually going to do a little bit different from our sequence notation, and I'm going to put in A6 itself. And so notice I've bolded the starting amounts. Actually, no, come to think of it, I'll put in A6 minus 1, so it's a bit closer to the sequence notation. There we go. So that's what we get. That's what we expect to get from the sequence notation with like an n minus 1. That keeps track of the starting amounts each year. And so that in year one, no time has elapsed since year one. So the number of times you're multiplying by little r is 0. And so you just get exactly the principal. All three of these numbers are equal. Then if I fill that down, it's going to match the starting amounts. If I wanted to match the ending amounts, then I wouldn't put the -1 here. Again, it's not the biggest deal in the world. The really important thing is we've got this connection that I'll put out here that in this case, it's going to get a little more complicated in the monthly case, but the multiplier or the ratio between two successive amounts, what we focus on when we're talking about geometric sequences, is just 1 plus the interest rate. So let's go back. That was a whirlwind review of how the sequence goes. So the key thing, as I pointed out before, is that geometric sequences are exponential functions, and that is compound interest in its simplest form. You want to think of those three things as the same thing, an application and two mathematical perspectives. Not that different. So what about our actual situation where we had something where we were not just sitting on a lump sum and letting that grow, we kept entering money over and over again. Here's how I like to think about that. And this is a cool thing because you can discover this, but I'm shortcutting it for this video. And I'm going to put in some really simple numbers here. $1, 100% interest rate, crazy good interest rate. In other words, they double my money every time they compound, just so we can see some familiar numbers that we've seen in other situations. And here's the trick. Every time I put in another lumps and another sum, here another dollar, I'm going to actually put it in a separate account. You can totally do that. You could open up separate accounts. They wouldn't like you very much, but you can totally do that. Now, what you really care about, say after year 5, is the total amount of money. In this case, that's $31. But we're going to see the pattern much better, as is often true, if we sort of overcomplicate it a little bit or keep things separate instead of mooshing them together. And so let's see what we get. Okay, we put in that first dollar, and if I never put in another dollar into that account, it's going to grow exponentially. This is exactly just a geometric sequence. And these are the powers of 2 in this case. Account 2, that put a dollar in, but 1 year later. And so that's going to be a geometric sequence. Same powers of 2, exactly the same numbers, but just staggered. And account 5, for example, was open in year 5, and account 10 was open way in year 10. So remember, the fiction here is the different columns with all these different dollars in their different accounts. But it really makes something, I think, more visually striking, which is, for example, let's go back to this $31 in year 5. Let's see what that sum is. It's the $1 we just put in, and that has been multiplied no times by powers of 2. It's the dollar we put in a year ago. That's been multiplied once. It's the dollar we put in 2 years ago, 3 years ago, 4 years ago. And we're adding these up. So notice, again, these are going horizontally from right to left. These are the terms of a geometric sequence because we knew they were the terms of a geometric sequence going top to bottom. And so the total amount, which we really care about in this situation, is exactly the sum of a geometric sequence, a finite geometric sequence. And that's this cool formula that we do know that there is a shortcut how to take the sum of a geometric sequence. So not surprisingly, we're getting one of our familiar sequences of numbers. This one was not something people see right away, but we've seen it. This is 2 minus 1, 4 minus 1, 8 minus 1, 16 minus 1, 32 minus 1, 64 minus 1, etc. And so we actually can get the formula. So let's go back to where we can do it more in mathematical notation. Okay, and so for example, just the numbers with that particular example. Remember, 1 plus 2 plus 4 plus 8 plus 16 plus 32. That was 2 to the next. We want to get the next power. This is 2 to the 5th. This is going to be 2 to the 6th minus 1. And of course, we're going to do this much more generally. Let's remember the formula: 1 plus r squared plus r cubed plus. Now, I am definitely going to take it up to r to the n minus 1. And this is a nice place for that to be n minus 1, because what we really care about is the right-hand side, and that has a little bit of a slicker thing. It's r to the n. Okay, it's all based on this guy. So the main thing that multiple accounts picture is supposed to tell you is that we actually, without even knowing it, when we do annuities, we are actually just summing up a geometric sequence. Now, of course, we're not just going to put in $1 in general. We're going to put in some amount, A1, and that's going to multiply everybody. Let's see if I can do a copy and paste here. And I could show you that in the Excel in just a second. Okay, and that is going to be the formula. And as long as we know what little r is, what a1 is, what n is, we're going to get it. So this video shouldn't be too long because we're really close to the end, and then I'll do a separate one with the monthly story. Okay, so here we go. Okay, so let's see. So here's that A1, if we made that $10, everybody just goes up by 10. It's never the complicated part. It's like the P in PERT is just a direct proportionality. It's just a multiplier. Of course, we could make this a more reasonable interest rate. And now we're seeing numbers that are more reasonable here. If we made this the $1,000, we're going to replicate exactly the numbers we were seeing on the other screen, the 2050, 3150, 250, etc. So let's get the formula. We just need to translate what we saw into Excel speak. So that regular deposit was the A1, and that's $B, $2, times parentheses. These are going to be really crucial. Okay, and then it was the multiplier, and I'm going to use the fact that I've pre-calculated the multiplier, the little r, from the big R, the interest rate, G2 to the, and now this really is to the n. It's to the number of years, and so that's going to be A6. No -1 there, definitely not. But then, after I take the power outside of that, you do get a -1 for a very different reason, divided by $G, $2, -1. Let's see if it works. Whoa, so far so good. Extra decimal place. Hey, 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 not too shabby. Okay, and of course these extra decimal places don't show up, that third one doesn't show up in money, but that's what it would be mathematically. So it turns out that the annuity story is exactly something that motivates you to think about the summation of a finite geometric sequence.